We're starting chapter 8.1 through 8.3 here today, which is the chapter on thermochemistry, where thermochemistry is the study of heat effects associated with chemical reactions. We're going to begin with principles of heat flow, and I wouldn't doubt that if you've had some physics that you've seen some of this before. We're going to talk about calorimetry, which is the laboratory technique that's used to study thermochemistry and other principles of heat flow. And then we're going to get into enthalpy, where enthalpy is described as or defined as the energy stored in chemical bonds. So obviously this is very important when we're talking about the energy associated with chemical reactions. And then we'll do our normal review. Let's go ahead and get started. And our first review question asks us to determine whether each of the following is polar or non-polar. Well, remember, to be polar we need two things. We need polar bonds and an asymmetric shape. Well, I see two different elements in krypton difluoride, so I do have polar bonds. Okay, what is the shape of this molecule? What is the geometry? Well, I have an AX2 something. Are there any non-bonding electron pairs? Well, krypton's a central element. It has 8 outer electrons. 2 are being used to bond, so that's 6 that aren't. And so there's 3 non-bonded pairs. And you may recall that an AX2E3 gives us a linear geometry, which is symmetric if the two attached atoms are the same. And if you're a symmetric molecule, you are nonpolar. In sulfur hexafluoride, we do have polar bonds. Sulfur is a central element. It has 6 outer electrons. It's using all 6, so this is an AX6 geometry. And now, we only have one thing attached to that sulfur. What does that tell us? That it's symmetric. And symmetric always means non-polar. So just by seeing there was only that one thing attached to the central atom, we could tell that this is going to be non-polar. In bromine trichloride, we do have polar bonds. Bromine's a central element. It has 7 outer electrons. 3 are being used to bond, so that's 4 that aren't. So this is an AX3E2 geometry. And that gives us a T shape. Now let's just look at AX3E2. Is this one of the two shapes that has non-bonded electrons and yet is symmetric? No. AX2E3 and AX4E2 would be those that have non-bonding electrons and are still symmetric. This is one of the many other times when a non-bonding pair of electrons ruptures your symmetry to give you a non-symmetric shape and hence a polar molecule. For the sulfide ion, I have polar bonds and I suspect resonance, so I need to draw one of these. And now I can see I have an AX3E geometry, and this gives me the triangular pyramid, which is not a symmetric shape. And because the sulfide ion is asymmetric, this is a polar molecule. For the thiocyanate ion, I do have polar bonds. Let me go ahead and draw one so I can see this is an AX2 geometry. And if those two X's were the same, this would be symmetric. But those two X's are not the same. And as we have the vast majority of the time, 2 different things attached gives you an asymmetric shape. And so the thiocyanate ion is polar as well. Okay, now we're going to determine the molecular orbital hybridization of our central element, and then we'll determine the number of sigma and pi bonds. Okay, now it always helps to draw one of these. You may get away with not drawing it, and to not draw it, I would go about this like this. My central element is carbon. It has 4 outer electrons. All 4 are being used to bond, so there is those 4 chlorines only around that central carbon. So I have 4 regions of electrons. That takes 4 orbitals, and so my S and 3 P's for sp3. And then I would see 4 single bonds for 4 sigmas and 0 pi's. Now, that may have not really jumped out at you, so let's draw carbon tetrachloride. There's step 1, drawing your central element. Step 2, bring in your peripheral atoms. There's no leftover unshared pairs of electrons, so there is no step 3, meaning there is no multiple bonds. And now by looking at that molecule, I can see 4 regions of electrons around the central element. So again, that's sp3, 4 single bonds, so 4 sigmas. In carbon disulfide, I'm going to go ahead and draw this, and in doing so, I can see that I have 2 regions of electrons around my central atom, and that takes 2 orbitals, so that's going to be an s and a p, so that will be an sp orbital hybridization. And those 2 bonds, those 2 double bonds, there are 1 sigma each and 1 pi, for a total of 2 sigmas and 2 pi's. Could we have done this by saying carbon's our central element, has 4 outer electrons, all 4 are being used in bonding, which leaves us with just 2 regions of electrons, 2 double bonds, and we may have been able to see that without drawing it. But if it's not jumping out at you, do take a few moments to draw it. Okay, here's acetylene. I'm going to go ahead and draw acetylene. So there will be step 1. Here's step 2. I have leftover electrons, so I do have a step 3. And now around each of those carbons, how many regions of electrons do you see? 2. I hope you see 2. So an S and a P. How many sigmas? I hope you see 3. And how many pi's? I hope you see 2. Remember, a triple bond is 2 pi's. And hydrazine, there's step 1. There's step 2. We are going to have a step 3 since we have leftover unpaired electrons. And now around each nitrogen, I can see 3 regions of electrons, so that takes 3 orbitals, so sp and p for sp2. And I see 1, 2, 3 sigmas and 1 pi. Same question, same approach. I'm going to go ahead and draw this compound. Sulfur's my central element. There's step 1. Let's bring in those peripheral atoms. Obviously, I have to break open those non-bonded pairs of electrons. There's step 2, and there is no step 3 since there's no leftover electrons at this point. And I can see 1, 2, 3, 4, 5, 6 regions of electrons around that central sulfur, so that's going to take the mixing of 6 orbitals. So we begin with an S, then we have a P, and another P. So there's 4, a D, and another D. That brings us up to 6. So sp3d2, and those 6 single bonds mean 6 sigmas. For xenon tetrafluoride, xenon is our central element. I need to break open 2 of those non-bonded pair of electrons to accommodate the 4 bonds to the 4 fluorines. And now with this drawn, I can see 1, 2, 3, 4, 5, 6 regions of electrons, so that's again going to be sp3d2. And I count 4 single bonds for 4 sigmas. In chlorine trifluoride, chlorine's the central element. I need to break open 1 of those lone pairs to accommodate all 3 fluorines. And now I count 1, 2, 3, 4, 5 regions of electrons. That takes the mixing of 5 orbitals. So the first is an S, then we have a P, then we have another P, then we have another P. That's 4. We need to bring in 1 more. That'll be a D. So sp3d. And 3 single bonds for 3 sigmas. Until we see multiple bonds, there will be no pi's. Same question, same approach, and iodine is a central element. I need to break open 2 of those non-bonded pairs of electrons. And now 1, 2, 3, 4, 5, 6 regions of electrons. I have to mix 6 orbitals, so sppPDD, sp3d2, and 5 single bonds for 5 sigmas. And selenium tetrachloride, selenium is a central element. To accommodate the bonds to 4 chlorines, I need to break open 1 of those non-bonded pairs. Here I can count 1, 2, 3, 4, 5 regions of electrons around the central element, so that takes the mixing of 5 orbitals. So first is an S, then a P, then a P, then a P. That's it for the P, so on to the Ds. So sp3d, and 4 single bonds, or 4 sigmas. In bromine trichloride, bromine's the central element. I count 5 regions of electrons, so sp3d again. And this time we have 3 single bonds, so 3 sigmas. Okay, same question, same approach, and for nitrosyl chloride, I suspect, and I hope you suspect, resonance. If you suspect resonance, it's going to be hard to tell what your central element is doing without actually drawing one. So let's draw one. This is not one. This is essentially where we would always begin. And so how did we begin? Well, we already know that chlorine is not going to participate in the resonance. So let's just go ahead and count the 1 electron from the chlorine, the 5 electrons, and I'm only 1 from chlorine because it's participating in the bond. The other 6 are not. Okay, the nitrogen has 5 electrons. We're up to 6. 2 oxygens. There's another 12. That's 18 electrons, 9 pairs. So we need 1 to hold the nitrogen to the 2 oxygens and the chlorine. So there's 1, 2, 3. Again, just putting in the bonds between the central element and the peripheral atoms. And then 4, 5, 6 for those pairs of electrons going to the oxygen on the left. 7, 8, 9. Those 3 pairs of electrons going to the oxygen on top. And now, everybody but the nitrogen has 8 outer electrons. To accommodate the nitrogen, I'm going to bring down 1 of those non-bonded pairs from 1 of those oxygens. And now I have all that I need. I'm going to go ahead and draw the second, but I don't need to actually have it to tell I have an AX3 geometry. 3 regions of electrons around my central element, which takes 3 orbitals, so an S, a P, and another P, so sp2. And now I can clearly see 1, 2, 3 sigmas and 1 pi. And I recommend that you do some of these on your own. For dinitrogen oxide, again I suspect resonance, so I need to draw 1. So again, here I just put in the minimum of holding everybody together and then just started giving the peripheral atoms the extra electrons. So I just kind of came up with this real quickly, and now I don't have a resonance structure. Neither the nitrogen on the left or the nitrogen in the middle have 8 outer electrons. What can I do about that? Well, how about I drop down the electron pair that's being shared, or to be that electron pair that's loaned to the central nitrogen to give me that double bond to the nitrogen on the left. And let's break down another pair of unshared electrons for the oxygen to form a second bond. And that would give us 1. And that's all we need to see we have 2 regions of electrons around our central element. Let me go ahead and draw the other 2. And now, looking at any of these, we can see that there's 2 regions of electrons around the central nitrogen, so S and P. And in any of these, we see 2 sigmas and 2 pi's. So do expect your orbital hybridization, your number of sigmas and pi's, to remain unchanged amongst your different resonance structures. Okay, one more time, and again I suspect resonance, so I need to draw 1. This time I'm just going to draw 1. I have what I need. I can see 3 regions of electrons around the central element, so S and P for sp2. 1, 2, 3 sigmas, and 1 pi. Again, let me draw 1. 3 regions of electrons, so again that's going to be an sp2. 1, 2 sigmas, and 1 pi. Let me draw one of these. 1, 2, 3 regions around the nitrogen. So once again, sp2, 1, 2, 3 sigmas, 1 pi. One last example, the hydrogen carbonate ion, and I hope that you know to begin with the carbon in the middle and the hydrogen on the other side of one of those oxygens. In any oxo acid, the hydrogens are attached to the hydrogen. And now with this, we can see the carbon has 1, 2, 3 regions. Once again, sp2, and I count 1, 2, 3, 4 sigmas, and 1 pi. Could you have done this one without drawing it? And I think the answer is no. So plan on drawing these when you're asked. Give the orbital hybridization of the central element. Determine number of sigmas and pi's. Okay, on to new material, and we're starting a chapter on the study of thermochemistry, which is the field of study of the heat effects or the heat changes associated with chemical reactions. So we know that when you light a piece of paper on fire, lots of heat is released. Well, that would be an example of a thermochemical process. Now, let's define some of these things, and the first is heat, which is abbreviated by the lowercase letter of Q. Don't ask me why it's lowercase q, but there's the abbreviation for heat. Now, heat is one of the forms of energy, or is a form of energy, but it's specifically a form of energy where this energy is transformed or transferred between two different bodies, one at a higher temperature and one at a lower temperature, and heat always flows from the higher temperature into the lower temperature. So think if I have a hot piece of metal and drop it into some cold water, well, that heat from the metal is going to essentially flow from the hotter metal into the colder water, and at the end they would both come to equilibrium at the same temperature. Okay, so again, Q is heat. In this illustration, we can see as you heat up water, that energy is coming into your system of water. And if you turn off your hot plate and it starts cooling off by radiating out that energy, that it's cooling off and energy is going out. So again, on the guy on the left, I hope you can see energy is coming in. On the right, energy is going out. Now, let me define energy, and I'll go on to talk about energy out and energy in. First, the simplest way to define energy is that energy is the capacity to do work. So think of work. How much work you're doing would be a measurement of energy. Another definition of energy is a force applied over a distance. Now we're getting into something like physics. I'll let you get to your physics class to let them finish that conversation. Okay, we talked about energy going in and energy going out. And so that's all about the principles of heat flow. Well, we know that heat is going to flow from hot to cold, but let's also talk about the sign of the energy change that's associated with it. Now first, we have what's called an endothermic reaction. Endo means in. Thermic, that is energy, and so energy in, endothermic energy in. And if energy is in, then we're increasing our internal energy, and so Q for that process would be positive. Again, here, energy is flowing into your system from the surroundings. Then we have exothermic, and exo would mean out, so this is energy out. Here we are losing energy, our amount of energy is going down, and so we can think of Q as being negative. So again, energy coming into the system, Q is positive, energy leaving the system, Q is negative. And again, at this point, energy would flow from the system into the surroundings. Well, let's go back to endothermic, if the surroundings is providing the energy to flow into the system, then if its energy must be going down and the surroundings get colder. So think of holding a test tube, and in an endothermic process, the test tube is getting colder. If the test tube is getting hotter, meaning your surroundings are increasing in temperature, that's due to that energy that was released. So again, endothermic, energy in, surroundings are getting colder. Exothermic, energy out, the surroundings are getting warmer. So when we look at this picture again, what do we have for the water on the left? Energy in, endothermic, and the process would be positive. The illustration on the right, it's energy out, that's exothermic, and the sign of this would be negative. So endothermic positive, energy in, exothermic negative, energy out. So do note how the sign tells us the direction of the heat flow. Now let me introduce you to what's called heat capacity, abbreviated by capital C. We'll see a little c in a little bit. And this is essentially the energy required to raise the temperature of your system by 1 degree C. And it's going to have the units of some energy unit per some temperature unit. So joules per degree C, or maybe kilojoules per degree C. We tend to work primarily with degrees C here. And here is our primary equation for many of the problems to come. So think of this as our initial equation, and again, one of our big primary equations, which means one that we do a lot with, where Q is equal to big C times delta T. The heat of the process is equal to big C, the heat capacity of the metal you're heating up, for example, times delta T. And a delta is always where you finish minus where you began. So that's going to be your final temperature minus your initial temperature. Now do note the sign of the heat flow really is going to come from that delta T. C is always going to be positive. So when we have a higher final temperature, then we're going to generate a positive delta T and a positive Q. But if we have a smaller final temperature, then we're going to be left with a negative delta T, and that's how we're going to calculate a negative Q. I mentioned lowercase c, and this is what's called specific heat. So heat capacity, big C, that's for the whole system. Specific heat, this is the heat required to raise a single gram of your substance by 1 degrees C. And hence the units are different. For heat capacity, it's energy per temperature unit. For specific heat, it's energy per gram temperature unit. Expect it always to be joules per gram degree C for your specific heat. And when we look at our derivation of our primary equation, in this form, Q is equal to lowercase m times lowercase c times delta T. And so very often we're going to get big C from the product of lowercase m, the mass of your subject, and lowercase c, the specific heat of that subject. Well, the nice thing about specific heat is it's per 1 gram of that material. So we have specific heat for water, specific heat for pretty much any element, many compounds, etc. And so this gives you a constant for that particular subject. Whereas heat capacity is just to your own system. Okay, let's look at an example where we're asked how much energy is required to heat 25 gram sample of iron from 90 degrees to 150 degrees C, and we're given the specific heat for iron at 0.446 joules per gram degree C. Okay, where do we begin? Well, we reach for our primary equation. You always want to start with the equation that gets you the answer you're after. And our primary equation is Q is equal to lowercase m lower c delta T. Again, it's a very common primary equation, meaning the one that you're going to start with. And now what are we after? We're after Q. So this is already isolated for the variable we're after. And we actually have the mass of the water, we have the specific heat capacity, and we have what we need for delta T. So let's go ahead and plug it all in. So there's the mass of the iron, the specific heat of the iron, and the change in temperature of the iron. So what is the energy change or the heat change of your iron? 669 joules. Does that answer make sense? Well, first, what does that mean to be positive? That it increased its internal energy. Well, if you got warmer, you increased your internal energy. So yes, that endothermic process matches. So what you'll find is if your subject heats up, it's increasing energy, so endo. So Q should be positive. Now, what if this went the other way from 150 to 90 degrees C? Well, now it's going to be releasing that energy, and then it would be exo. And again, if it went from 150 to 90 degrees C, do note we're going to have the same number just with a different sign. Okay, next we're told gold has a specific heat of 0.129 joules per gram degrees C. When a 500 gram piece of gold absorbs 1 kilojoule of heat, what is the change in temperature? Okay, again, let's reach for our primary equation. Q is equal to lowercase m, lowercase c, delta T. You know, if you started with Q equals big C delta T and then recognize big C is little m times little c, we'd get to the same place. And now what are we after? What is the change in temperature? So we're after delta T. So let me go ahead and isolate that variable by dividing out the mass and the specific heat of gold. And now, do we have the specific heat? Yes, we do. Do we have the mass? Yes, we do. Do we have the heat capacity? Yes, we do. So we have everything to plug in here. Now, why did I put 1,000 joules instead of my 1 kilojoule? Well, this is essentially an illustration that supports how I've been saying you need to always keep track of your units. Even if they're not setting up a problem for you, they're there still to help you catch small mistakes. So what if we had put in no units at all? We just put in the 1 for the 1 kilojoule, the 500 for the 500 grams, the 0.129 for the specific heat. Well, we would obviously be 1,000 times too small, but we wouldn't catch that mistake. We didn't bring out the units. So that's my point here. Carry your units, and they'll help you catch small potential mistakes that pop up all the time. And so that helped us to recognize that we couldn't leave our energy in kilojoules. We had to convert it into the common unit of joules. And I come up with the final answer of 15.5 degrees C. Does my answer make sense? Well, this is a positive temperature change. Would I expect a positive temperature change if I absorbed heat? Absolutely. Do note if the problem had said released at 1 kilojoule, everything would be the same except for that 1,000 joules will be negative. Released energy, your sign is now negative. Absorbed energy, positive. So again, the signs of your energy tell you a whole lot. So we need to be paying special attention and being very careful with those signs. Okay, on to calorimetry, and this is the technique, the laboratory technique that we use to actually measure heat flow, or the energy changes in chemical reactions. Now, we carry out these calorimetric measurements in a tool known as a calorimeter. And a calorimeter comes in two different types. Both of them essentially would end up being an apparatus of a known heat capacity, so we know what that big C is. And this is an example of what's called a bomb calorimeter, and do note we have this bomb that's in the middle, that's the guy in the middle, where we actually conduct the reaction. We're actually doing a combustion reaction there, so the bomb would have been pumped full of oxygen, and then we have some wires to essentially ignite the reaction. And essentially as it burns, it's going to release that energy. The temperature of the surroundings is now going to go up. And so the surroundings here is still part of the system. That calorimeter is that interior water. And so do note we're going to have this surrounded by water so that the water absorbs the energy or provides the energy in the endothermic process. And the amount that this whole calorimeter would change a temperature unit would be consistent with a given amount of energy. So essentially, just like before, we know the energy for the change in temperature of this calorimeter, this tool, this system. And in the lab, we're going to use this high-tech device known as a coffee cup calorimeter. And often we're going to choose this because, one, it's nice and cheap. Two is that we need an environment that's more like this when we're doing reactions within water. Maybe we're doing some aqueous reactions, or maybe we're doing some heat changes, like throwing some hot metal in there or something like that. And we'll be doing some labs involving a coffee cup calorimeter. Do you know, if we know the mass of water in the calorimeter, we know the specific heat of the calorimeter, then the specific heat of the water, then we know the heat capacity of that calorimeter. Now, I want to point out that Q of the reaction is now going to end up being negative Q of the calorimeter. What this means is if the calorimeter absorbed 1,000 joules of energy, well then the reaction must have released that 1,000 joules of energy. So we'll find that these are equal in magnitude but opposite in signs, because if one is absorbing, the other one is releasing. If one is releasing, the other is absorbing. And so here is where you're going to be told the calorimeter changes temperature, not the piece of metal like we had in our previous example. So if you're wondering when does a negative show up, it's when you're actually dealing with the calorimeter. Our previous problem did not deal with the calorimeter, meaning we talked about how the piece of metal was heated up. Okay, now the heat of the calorimeter is equal to, and here's your same equation we saw before, Q of the calorimeter is equal to big C of the calorimeter times delta T, and hence Q of the reaction is equal to the negative of this big C delta T. Okay, let's look at an example. When a 5-gram sample of an unknown salt is added to 100 grams of water in a coffee cup calorimeter, it dissolves, and the temperature of the water drops from 25.0 to 21.0 degrees C. Assuming all the heat is absorbed by the water, calculate Q for the reaction system. And we're given the specific heat of water. Note how huge that number is compared to the other specific heats. Water has a higher specific heat than anybody by far. And that's a good thing, because that means that these huge oceans that we have on planet Earth are great for maintaining a constant temperature here on planet Earth. Nothing else even comes close to the specific heat of water. Okay, let's get to the problem. What do we have going on? Well, we're given the amount of water, so we're actually being given big M and, little m and little c here. And let's see, it looks like we're dealing with same primary equation. Q of the reaction is equal to Q of the calorimeter, which is equal to negative big C of the calorimeter times delta T. Do we have big C of the calorimeter? No, we have the mass of the water, and we know the specific heat of water. So as so often is the case, big C is actually the product of the mass of water and the specific heat of water. Whenever you have a coffee cup calorimeter, you can count on that. And so here's the mass of the water, the 100 grams, specific heat of the water, the 4.18 joules per gram degree C, and our change in temperature. We finished at 21 degrees C, we began at 25 degrees C. Again, it's always where you finish minus where you began. And that gives us a positive 1,672 joules. Does our answer make sense? Well, does that positive make sense? Well, let's see, the water's temperature went down. Well, if the water's temperature went down, it used that energy to feed the energy required for the reaction. So yes, if the temperature of the water goes down, think of that test tube again, test tube gets colder, endothermic energy in, positive. If the test tube got hotter, the surrounding gets hotter, energy out, exothermic, your sign will be negative. So yes, positive matches. Okay, now I want to introduce you to enthalpy, which is actually the term that we use to describe, or as defined as the energy that's stored in your chemical bonds. Now, we use an H because sometimes this is referred to as the heat of a reaction. So if we look at a chemical reaction, essentially what we're going to find is we have an energy change. Now, working along with what we've already seen, we're going to find out that delta H, our change in enthalpy, remember we're talking about a chemical reaction, which is a change, so we're definitely dealing with a delta here. Delta H, your change in enthalpy, is equal to the Q of the reaction, and of course, that's equal to negative big C of the calorimeter times delta T. Let me also remind you that delta H, your change, is always where you finish, so that's going to be the enthalpy stored in the bonds of your products, minus delta H can be minus H of your reactant. So again, delta H, your change in enthalpy, will be where you finish, the enthalpy stored in your bonds, the products, minus the enthalpy stored, or the energy stored in the bonds of your reactants. So again, where you finish minus where you began. Now that should make it real easy for us to see that if we have an exothermic reaction, like the one where methane burns in oxygen, that's what we see here, methane is burning in oxygen, that we would have an exothermic reaction, and hence delta H is negative. Remember, if Q or delta H is negative, then energy is being released, and this is an exothermic reaction. Now, since we're talking about energy being stored in bonds, what does that mean to be negative? Well, let's just go back to the previous equation. H of the products minus H of the reactants. For that to be negative, H of the reactants must be the larger number. In other words, the energy stored in the bonds in the reactants must have been bigger than the energy stored in the bonds of the products. So you started with more energy than you finished with. That excess energy is what's liberated. So we see in an exothermic reaction, where both Q and delta H are negative, then the energy stored in the bonds of the products are less than the energy stored in the bonds of the reactants. Whereas in an endothermic reaction, where energy is coming in and delta H and Q are both positive, then the energy stored in the bonds of the products is now greater than the energy stored in the bonds of the reactants. We got to pump some energy in there. So I hope you can see how endothermic and exothermic match up with positive and negative. So don't ever forget the principles of the signs of heat flow. Okay, let's do an example. 2.5 grams of potassium bromide dissolves in 100 grams of water in a calorimeter. The temperature drops from this to that. What is the enthalpy change in kilojoules per mole? So now we're being asked specifically for the unit of kilojoules per mole. So what's the enthalpy change when specifically in kilojoules per mole when potassium bromide dissolves in water? And there's the heat capacity of water. Okay, now I'm going to go ahead and tell you that we're going to first use our equations and calculate the enthalpy based on that 2.5 gram sample. And then from there, we're going to convert that into the enthalpy per whole mole of the sample. So let's identify what's our primary equation. And I hope you chose delta H of the reaction is equal to Q of the reaction, which is equal to negative Q of the calorimeter. And hence, delta H is equal to negative big C of the calorimeter times delta T. How many times have we seen this equation? This is by far one of our most common primary equations, so don't forget this guy. Okay, do we have big C? No, we have little c, and we have the mass of the water, and whenever you have a coffee cup calorimeter, meaning a calorimeter based on water, big C ends up being the product of the mass of the water and the specific heat of the water. And we do have the mass of the water, we have the specific heat of the water, and we have the numbers for the change in temperature of the water, and this is all about the calorimeter. And so, mass of the water 100 grams, specific heat of the water 4.18 joules per gram degree C, and the temperature change. And when I put this on my calculator, note that's going to be a positive quantity. Is positive correct? You should always double check that sign. It's just so easy to make a mistake on the sign. Does that make sense? Well, if my enthalpy for the reaction is positive, the test tube must have gotten colder. And indeed, we can see, yep, the temperature went down, so that looks correct. Now, how are we going to get our answer in kilojoules per mole? Well, for this portion of the calculation, we're going to use our units. We're just adjusting this unit to that. We know we're using our units. So equals kilojoules per mole. For step 2, what are we going to start the calculation with? And I hope that you're able to see it's going to be the just determined 416.3 joules per that 2.5 grams sample of potassium bromide. All right, I think we're in good shape. On to step 3, out of joules, can I go to kilojoules? Simple metric conversion there. Out of grams, can I go to moles? You can always go from mass to moles. That's your most common calculation in all of chemistry, going back and forth between grams and moles. Okay, 1 kilojoule, 10 to the positive 3rd joules. And for potassium bromide, I have the sum of potassium's molar mass and bromide's molar mass for 119.0 grams per mole. And when I put this all on my calculator, I come up with 19.8 kilojoules per mole. Does my answer make sense? Well, I've already identified that. The positive sign makes sense. Does 19.8 make sense? Well, it's kind of hard to tell if that's the correct number. I can go back and double check my numbers to see that it's right. But I really can't say for sure without doing so if that 19.8 is correct. But at least I've identified that the sign is correct. And that's a common mistake, so let's at least try to catch those common mistakes. Okay, next one, 5 milliliters of ethyl ether, sometimes called diethyl ether, is burned in a bomb calorimeter. The temperature rises from this to that. The heat capacity is 10.34 kilojoules per degree C, so do note how this heat capacity is in kilojoules per degree C. You've seen others in joules per degree C. What's the enthalpy change per mole of ethyl ether? So we're going to be looking for our answer in kilojoules per mole. So this is going to be very similar to what we did before. So again, we're using equations to get us started. In our primary equation, delta H of the reaction is equal to Q of the reaction, which is equal to negative Q of the calorimeter, which is equal to big C of the calorimeter times delta T. Again, how many times have we seen this as our primary equation? And let's see, do we have big C? Yes, this time we're given big C. And we're given the initial and final temperatures. Make sure you put them in the right order. What if you put them in the wrong order? You're simply going to have the same number with the wrong sign. So again, make sure you put them in the right order. And I come up with negative 167.5 kilojoules for that 5 milliliter sample. Does a negative make sense? It's burning. The environment is getting hotter. Indeed, it makes sense that the sign is negative. Exothermic energy is being released. The environment's getting warmer. Okay, just as before, we need to use our units to convert that into the appropriate unit of kilojoules per mole, starting with the just calculated kilojoules per 5 milliliters of the diethyl ether. We already have our numerators units, so we need to take care of our denominators units. So, can we go straight from milliliters to moles? And I might start scratching my head here, wondering what's going on. I can't go from milliliters to moles. Well, when I look up at the problem again, oh, I was given the density. Now I see why I was given the density. To get from milliliters to grams. And then from grams, I can go to moles. It might have helped if we got stuck with milliliters to ask, how do we think we're going to get the moles? From grams. Can I go from milliliters to grams? Oh yes, I was given the density. Okay, let's put in those numbers. 7.14 grams per each milliliter. Molar mass of the diethyl ether, we have 4 times 12.0, 10 times 1.0, and 1 times 16.0, which adds up to 74.0 grams per each mole. And when I put this all on my calculator, I come up with negative 3,472 kilojoules per mole. Note that's a huge number compared to the last problem, so I might scratch my head and say, does that make sense? Well, when you're burning something, there tends to be a lot of energy involved. And so I'm going to say, yeah, that kind of makes sense. Again, when something's burning, lots of energy is involved. Okay, let's review some things that we've just gone over. Which of the following statements are true? The value of Q is negative in an endothermic process. No, the value of Q is negative in an exothermic process. Remember, positive when energy is coming in, endo, negative when energy is going out, exo. True or false? At constant pressure, the heat flow of a reaction equals the change in enthalpy, and we've seen that is true. The reason we're talking about, or we put in the condition that there's a constant pressure, is because we want to have to avoid dealing with energy that's being used for work. We're going to talk about that at the end of the chapter, so we will get to that. Okay, next, true or false? Delta H for reaction is equal in magnitude but opposite in sign to delta H for the reverse reaction, and that should totally make sense. If I'm absorbing 100 joules in the forward reaction, then it should make sense that I would be releasing that 100 joules in the reverse reaction. So sure enough, and we should catch this, that a forward and reverse reaction, the enthalpy change is equal in magnitude, but just opposite in sign. So negative 100 joules in the forward direction, positive 100 joules in the reverse direction. Okay, true or false? Enthalpy is a state function. I haven't talked about this yet. A state function means it doesn't matter how you get from point A to point Z. It just matters what is your condition at point A and point Z. And sure enough, enthalpy is a state function. We can just look at what's the enthalpy in the products, subtract the enthalpy in the reactants to get our enthalpy change. We didn't need to worry about steps that were involved or anything else like that. So again, a state property means it doesn't matter how you get from the beginning to the end. It just matters what is your condition at the beginning and the end. True or false? Enthalpy change is dependent upon the number of steps in a reaction. And the answer is no, following what we just said. As a state function, it doesn't matter how you get from A to Z. And true or false? The enthalpy change of an endothermic reaction is positive. An endothermic reaction, indeed, is always positive. Energy in, positive. True or false? Heat flows from the system into the surroundings in an exothermic process. In an exothermic process, energy is being released from the system, and it's going to be released into the surroundings. So essentially, the surroundings temperature is increasing. So indeed, yes, the heat flows from the system into the surroundings in an exothermic process. So true. And true or false? The value of Q is positive when heat flows into a system from the surroundings. Okay, if the heat is flowing from the system into the surroundings, I'm increasing my internal temperature, and this is endothermic, and indeed that would be positive, so true. Enthalpy is a state property, state function. We already answered that, yes it is. And true or false, in an endothermic process, heat flows from the surroundings into the system. In an endothermic process, indeed heat flows from the surroundings into the system. So the surroundings get colder, so think of that test tube getting colder. Okay, if the same amount of heat is added to 1 gram of each of the following substances, which substance will undergo the largest temperature change? Now, obviously we can go ahead and actually calculate the temperature change for each of these, or we can use a little bit of logic. What is going to end up giving me the greatest change in temperature if I'm adding the same amount of energy to 1 gram of somebody with a high heat capacity? Again, that means a lot of energy is required to change a degree C, or with a very low heat capacity, which means a much less amount of energy is required to change 1 degree C. And I hope that you recognize that it's the smaller number, the smaller specific heat, that's going to generate the greater change in temperature. Okay, we're told that aluminum has a specific heat of 902 joules per gram degree C. How many joules of heat are required to change the temperature of 8.5 grams from 25 to 93.4 degrees C? Okay, well, what's our primary equation? Same one we've seen for a long time. We're not dealing with calorimeter here, so we're not dealing with that negative that you would see if this was a calorimeter problem. So do note why there's no negative here, but there would be if there's a calorimeter. I hope that helps you to see the difference between when the negative shows up and when it doesn't. Okay, we have the mass, we have the specific heat, we have delta T. So we actually have everything we need to plug in. Note how grams cancel and degree C cancel, leaving you with the appropriate unit of joules. Okay, I come up with a positive 524 joules. Does that positive make sense? Well, let's see. I increased in temperature. That definitely matches an increase in heat, an increase in energy, and hence a positive Q. Okay, the heat capacity of 5 grams of iron is 2.23 joules per joules per degree C. How much heat is required to heat the iron by 50 degrees C? Okay, our primary equation, Q is equal to big C times delta T. Remember, this is by far the most common primary equation. And since we're dealing with 5 grams of iron and we're already told its heat capacity, there's our big C right there, the 2.23 joules per degree C. We're told that the temperature increases by 50 degrees C, so 50 minus 0 would tell us that's a positive 50. And we generate a positive 112 joules. Does the positive make sense? Yes, you're increasing your temperature. That's definitely going to match a positive Q, a positive heat change. Okay, next, 35 joules is required to heat 50.3 grams of mercury by 5.00 degrees C. What is the specific heat of mercury? Okay, let's go back to our primary equation. Q is equal to lowercase m times lowercase c times delta T, because what we're after is lowercase c. So let's isolate lowercase c by dividing out lowercase m and delta T. Here's lowercase c isolated. Let's go ahead and bring out the heat, the 35 joules. The mass, the 50.3 grams. The change in temperature, 5 degrees C. And do note the units that it gives us. Joules per gram degrees C. Just what we would expect and need for specific heat. Okay, we're told that commercial cold packs consist of solid ammonium nitrate and water. So think of those cold packs. They get cold when you break them open. Essentially what you're doing is you're making it where the ammonium nitrate can dissolve in that water. The ammonium nitrate, NH4NO3, ammonium nitrate dissolves, when it dissolves, it absorbs 330 joules of heat per each gram of the ammonium nitrate that's dissolved. And now in a coffee cup calorimeter, 4 grams of the ammonium nitrate is dissolved in 75 grams of water. What is the temperature change out of the water? Okay, now let me go back to the line that says in a coffee cup calorimeter, 4 grams of ammonium nitrate is dissolved in 75 grams of water. Well, that 4 grams is ultimately giving you the energy. We know the energy per 1 gram, so this is giving us the energy for that mass, that sample of 4 grams. And then the 75 grams of water tells us m, lowercase m, for the mass of the water and the heat in the calorimeter. So Q of the reaction is equal to negative Q of the calorimeter. Negative Q of the calorimeter is negative big C of the calorimeter times delta T. And we're not really given big C, as so often is the case. We're given little m and little c, and their product gives us big C. Okay, and now, what is the temperature change? So let me isolate delta T. Let's divide out negative lowercase m of water and lowercase c of water. And now let's plug everything in. Q of the reaction is what? Well, we have 4 grams of ammonium nitrate at 330 joules per gram. So I'm going to go ahead and multiply those. Do note how that grams cancel to give us the units of joules. Lowercase m, the mass of the water. Lowercase c, the specific heat of the water. So we have everything. And let's investigate. Do all units cancel? Yep, all units cancel except for degree C, the unit that I need. And I get a negative number. Does that make sense? Should my temperature go down with a cold pack? Absolutely. Okay, a chemical reaction in an open calorimeter rises the temperature of the calorimeter from this to that. By the way, being in an open calorimeter, your pressure is going to be constant. So that's another way of telling you that no work is being done. Oh, it even says without changing the pressure. Okay, if the heat capacity of the calorimeter is, calculate the enthalpy change for the reaction. Okay, what are we doing here? Well, we do have a calorimeter, and we're talking about enthalpy. So our primary equation, delta H of the reaction equals Q of the reaction. We know Q of the reaction is equal to negative Q of the calorimeter. And we know that's equal to negative big C of the calorimeter times delta T. Do I have big C this time? Yep, I sure do. So let me go ahead and plug that in, along with my temperature. My temperature's initial and final. And I went ahead and put that on my calculator and generated the answer of negative 24.6 kilojoules. Does that sign make sense? I mean, I really want to know, does the answer make sense? But I'm looking at the sign. Again, I hope I'm getting you used to asking and answering, does my answer make sense? Does it make sense that this is negative? Well, let me see. Negative would be exothermic, so the surroundings should have increased in temperature. Yep, that's what we got. So, yep, that does give me an answer that I feel comfortable with. What about the 24.6? I really don't have a lot to go on, so I'm just going to go with that. That's okay. More than likely, if I'm going to make a mistake, it's going to be with a sign. I mean, yes, I might make a mistake with a number, but more than likely, it's going to be with the sign. That's going to be the one I'm going to be looking at first to see if I've got it correct. Okay, that concludes this lecture where we had our introduction to thermochemistry, the study of heat effects and chemical reactions, or heat exchanges, you might say. When it came to the principles of heat flow, remember, if energy is coming in, we're going to have a positive heat. If energy is going out, we have a negative heat. And so in and out essentially tells us positive or negative, or positive and negative tells us in or out. Calorimetry was the study of these heat effects, and essentially it's also the laboratory technique that we would go in the lab and make these measurements to make these determinations. And then lastly, enthalpy is the term that's used to refer to the energy that's stored in chemical bonds. So far, until we got to enthalpy, we're talking about heat, which could apply to things that aren't chemical reactions. But we want to start taking this a little bit further and start talking about that heat, that energy that's associated with chemical reactions. So again, I'll remind you, enthalpy is the energy stored in chemical bonds. And so when your reactants turn into your products, we have new bonds. And so it would be the, remember, delta, where you finish, the bonds in your products, minus where you began, the energy in the bonds of your reactants. And we'll be doing a lot more examples with enthalpy in upcoming lectures. Okay, so that concludes this lecture.